Okay, so welcome to the second day of the Teachers as Scholars series on using Fibonacci numbers and whatnot as a springboard to try to do fun stuff. And so what I want to do today is just continue talking about math games. There was a comment that we have somebody here who does fractals, and so I will quickly adjust to do a game that involves fractals. The math for that is a little bit more intense, but you seemed good last time, so you don't need to understand everything to play the game, but it helps to see a little bit of what's going on. So we did the I Love Rectangles game before. I love rectangles. Let's do another rectangle game. So what we'll do is we will do, if I give it the name that might give it away, I will do another rectangle game. And I just realized it is probably not displaying it over here yet. So, yeah. Just reconnect this. Here's the cable. Okay. And so there's an amazing number of rectangle games you can play. So hopefully this will toggle over. Okay. So I have a lot of slides for this, but rather than doing slides, I'm going to just draw it on the iPad and project that because I think it's a little bit more interactive to do it this way. So I'm going to take a rectangle and I'm going to draw a bunch of equally spaced horizontal lines and then a bunch of equally spaced vertical lines. And then it's two players. Whoever goes last wins. And on your turn, you draw a line from an exterior region to an exterior region going either straight down or straight across. I'm not going to really worry too much about explaining what it is. I'm going to just play the game once or twice and figure it out like that. So for example, I can go straight down. Actually, might as well use a thicker marker. I can go straight down like this as I'm going from an external to an external. Now it's blue's turn. Blue can't go like this all the way because it's crossing a colored line. So as soon as you hit a boundary, a colored line, you have to stop. So blue could go down like this, that would be valid. Blue could go all the way like this until it hits the red line, that would be fine. You don't go on the external, those lines are already done. So let's say blue chooses to go like this. Now it's red's turn. And so red could choose to go like this from one colored line to another, that's fine. Blue could go like this, whoops. Blue could go, I somehow lost the blue. Blue could go like this. Is it clear how the game is played? Mm-hmm. And then legal move or illegal move for red? Illegal, good. But if I stop over here, it's legal. And so your blue goes, red goes. Oops. Keep forgetting to go to the thick because I almost never use the thicker lines. Can blue cross a blue line? Blue can cross a blue line? No. Nor can blue cross a red line. You can't cross any colored line. You start from someplace that's external. And so I think I had just red went, so now blue goes, now red goes, and now blue goes. So player 2 wins. Okay. Everybody's clear on how this is played?
No, what is the object?
Object is to move last.
Oh. So you wouldn't, since it has to be external, you couldn't do that middle one.
Oh, sorry, we missed that one. Thank you. Sorry, I did not see that one. So it's not player 2 who wins, it's player 1. And we should turn this into red because it was player 1 who won. So
you don't have to start external.
Well, the initial move has to start from an outside. And then once you start playing, you can start from an outside, you can start from a colored line. You can't cross something that's been colored. If you want to try to make it maybe easier to visualize, we could take a board like this, and I'll start off with the outside colored black. And then I'll just put, and I'll just put in lines like this. And so you can see now that the outside has been, colored, and I can't move over there. And so now maybe red comes down. So red comes down like this, and then maybe blue comes down like this and has to stop because it hits a colored line. So if you want, if I view the outside as colored black, you're going from a colored line to a colored line, and you can't cross a colored line. So that might be the simplest way to describe it. Color the outside black, and you move from one colored line to another, and you can't cross. And so if red goes like this, now blue could go from the red to the red. And you keep playing until someone wins. Okay? So last to move wins. So I will play anybody right now. I'll let you choose if you want to go first or second. And if you win, I will give you $1,000. Now, something should make you suspicious.
Yeah.
So why are you suspicious? I'll let you choose if you go first or second.
Because you played many times. So you have a strategy.
I
A winning.
absolutely have played this many times, but I'm letting you choose if you want to go first or second.
Are you going to choose the board size or no?
I'm letting you choose if you want to go first or second.
It doesn't matter.
Well, I have not said what board we're playing on. Once you decide if you want to go first or second, I will then show you what board we're playing on. So what's nice is I volunteered in my kids enough in their classes enough times over the years that by the time they got to 4th or 5th grade, they realized every game with me was rigged. So what you can do is you can start assembling data. And one of the things I love when I do this with young kids is let's get some data. All right. So does anybody want to play me right now?
Sure.
Sure.
I'm ready to lose.
I do. I'll draw the board first and I'll let you choose. Okay. So would you like to go first or second?
I will go first.
Okay.
Thank you.
You're welcome. Thought you would do that. No, the reason I actually thought he would do that is I drew a 3x3 board. So by rotating things, there's really only one move you can do. So I knew you would have to do that as your first move.
All the way across.
Well, all the way across is the same. All the way across on the bottom is the same as all the way across on the top. And by rotating it 90 degrees is the same as the two verticals. On a 3x3 board, because of the symmetry, you have no choice. And so I can symmetrically respond to you by going right above. Now I have a suspicion of what you're going to try to do next.
I cannot.
Nope, because that's an external.
Okay.
You have to go from colored to colored.
Okay.
Okay. And now what I'm going to do is I am going to symmetrically respond to you. And you can see where this is going.
Yeah. Here?
Well, this is an external wall. You can't go there.
So I only can make an internal.
You only have 4 moves left.
And these will count?
That will count.
Okay.
So that's one possible move.
So it's about symmetries.
So over here, I'm going to respond symmetrically.
Okay.
And I will respond here. And so player 2 wins. Thank you. So what do you think was key to my strategy?
Design the board.
Designing the board, but in particular, so mirroring, right? So some kind of symmetry. And I know we have at least one chemist here today, and symmetry is big, right? Should we see what happens if I don't use symmetry?
Sure.
You want a rematch?
Yes.
Okay, so now let me finish drawing the board. I'm going to do your opening move for you because we agree that there's only one choice you have, right? And I'm going to respond differently. I'm not going to do anything symmetric. Now, I might be able to recover from this.
Can I make this move?
Yep. And you have to go all the way down. So a mistake that a lot of people make when they're playing is a lot of kids would just move to there and stop. Or a lot of kids would move just to here. Stop. You've got to go from colored line to colored line. You can't stop part way. Okay. I'm going to continue to be, I'm going to be as asymmetric as possible. I'll go there. This is why it's a lot more fun to do this than to have slides. Okay. I'll go there.
But
I can't. Good. I was seeing people. That's an illegal move for me. I have to go all the way across.
now I see that you've won.
Yes. And so now I will go here.
So you move the asymmetry.
Player 2 wins. Symmetry, not necessarily important. Even though I'm writing in blue, that was a red herring. You know, I deliberately do stuff like this when I'm teaching to try to get people to focus on the wrong thing. Is that, you know, there is nothing in my strategy that depends on symmetry. So let's gather some data. So everybody break into groups of 2 and play the game 10,000 times with various boards and report back to me. Okay. So length, oops, I should be doing in the neutral color. So let's do length, width, winner. So you give me a length and a width, and I will simulate 10,000 games randomly on my computer and report how many of them were won by each player.
Does the board have to be symmetric? Does
Nope.
Okay.
So give me a dimension for the board.
2 by 2.
2 by 2. Okay, my computer's chugging away. Player 1 won every single time of the 10,000. Anybody else want to give me a board size? 3 by 5. I had pre-programmed that. Player 2 won every single time.
You did one that was 1, 2, 3, 4 by 3.
And so let's have the convention that the length is always the small of the two.
Okay.
Just because, you know, 3 by 4 is the same as a 4 by 3.
Yeah.
So we might as well just do the data like that. The computer. Yeah, it might look suspicious that my hands aren't actually touching the computer. Is 1, 1, 1 every single time. Let's do, you know, 4 more datas, 4 more board sizes.
5 by 7.
5 by 7. Player 2 won every single time.
Interesting.
Even and odd thing.
So it could be. So test. People know the Queen Anne's Kingdom game. You know, it's how do you get out of Queen Anne's Kingdom, and you have to answer all the questions correctly. So there are feet in the kingdom, but no legs. People have boots, but no shoes. And you keep getting, you know, eventually you start to figure out what the pattern is as to what is and what is not in. So you have just conjectured that there's an even oddness. So give me some additional data to test your even oddness.
10 by 10.
10 by 10. Player 1 won every single time.
So even if the sum of the width and the length is even, then player 1 wins.
Could be. I mean, again, I will give you more data.
But 3 by 4 sums to 7.
3 by 4 sums to 7.
Oh, yeah.
What about 7 by 6?
So we'll do 6 by 7. Player 1 won every single time.
As long as one of the lengths is one of the dimensions is even.
Ah, so now you're rephrasing it. So now, so what if just one dimension is even? Okay, so give me another one to test this. See, this is what I love is you can start making conjectures and the students can try to figure things out.
4 by 9.
4 by 9, play a 1-1 every single time.
What about 5 by 5?
5 by 5, play a 2-1 every single time.
Number of squares.
I'm sorry?
Number of squares.
Could be number of squares, odd and even. Now, what's interesting right now is the only times play a 2 have 1. What can you say about the board sizes?
2 odd numbers.
Right, but they're more than just 2 odd numbers.
They're 2 apart.
They're 2 apart, or they're next to each other, or they're the same. Or what else? What can you tell me about the numbers 3, 5, and 7? They're prime. So maybe it's not just that they're odd, but maybe it's that they're primes. So what could you do?
6 by 6.
So 6 by 6.
Sorry, 7 by, no. 2 by 2.
Like we've already done 2 by 2. But if it's maybe that they're odd primes, how could you test if it matters if they're odd primes?
Try odd non-prime.
Try an odd non-prime. So what's a good odd non-prime?
9 by 9.
9 by 9. And play a 2 wins. So that's enough to show that it may not just be that they're odd primes. So does somebody want to formulate a conjecture? Player 1 wins if so what rule would you use to determine? So can you associate some special number to these dimensions? So you feel like even an odd comes into play, right?
Yeah.
What properties do you have of a rectangle? Length times width is area. So you have area and perimeter. So perimeter didn't work. We thought about perimeter. It was the sum odd. But we could look at the area. I'll do mod 2. The remainder when you divide by 2, is it even or odd? 2 and 2 is even. 3 and 5 is odd. 3 and 4 is even. Odd. Even. 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 Odd. Odd. And so the only times player 2 wins is when the area is odd. And every other time player 1 wins. So player 1 wins if area is even, else player 2. Now, when you do this with kids, this is a great activity to do with kids. I do this typically with your 4th graders, but I think it can be done much younger. The most difficult thing is the kids cross lines when they shouldn't, because you have to make sure they move legally. And they can gather the data and then you put it on the board and you start to see when do you have enough to sniff out the pattern. Now, what's interesting is that there is no strategy. If it's an even board, player 1 will always win. If it's an odd board, player 2 will always win. When I start doing things such as I'm going to respond symmetrically, I'm just misleading. I'm trying to make the kids think that I have a strategy so that they then do certain things and then I can do other things later. You know, like a magician, you want them looking at the wrong things. But as a teacher, then eventually you have to have them look at the right thing. So I'm going to prove to you now the conjecture theorem. Conjecture is true. Proof. This is the HersheyBar game. I just realized I probably should have bought Hershey bars today rather than M&Ms for something like this. I'm not sure if legally I'm allowed to use the HersheyBar name, but let's imagine we have a block of chocolate. And in the first move, we come down like this. Oops. Right, that was the first move. What that really does, I'm sorry?
Let's make it every day.
It makes it into two boards. So now we have a 3x3 here, and we have a 1x3. You can't move on both boards simultaneously. Where do you want to move next? And I can draw it down if I wanted to like this to just show that that's already been taken, doesn't matter. I should really have this whole thing outlined. So it's going to look like this. I now have two smaller boards. Which board? Oops. Hello? Okay, perfect. Yep. Okay, yep. Just somebody in the waiting room having technical difficulties. So I am glad I took the call. Okay. So which board do you want to move on next? The 3x3 or the 1x3?
1x3.
1x3. And so it doesn't really matter where you move, so I'm going to move for you. And let's say you chose to move here. I keep forgetting when I switch the size, it changes the color to I think what the color was before. No, it doesn't. Okay. So now we would have something like this. We would have, and then we would have two things like this. And so, this one, oops. So this one would still look like this. I would have like this, would have the red here, and then you've just moved like this. Notice this is move 0, we have one piece. Now we take our move, now move 1, 2 pieces. Move 3, I'm sorry, move 2. We have 3 pieces. Every time you move, what happens?
You get an additional piece.
You get an additional piece. So every move, get an additional piece. If it is L by W, have L times W pieces at the end of the day. So takes LW minus 1 moves. Start with player 1. If LW minus 1 is odd, then end with player 1 moving. Else with player 2. So player 1 wins if LW is even, else player 2. So we don't need any high-level mathematics to analyze this game. And there's a really nice principle lurking in the background. The key observation is every time we move, we increase the number of pieces. There is no strategy that I need to play. It's just always going to be the case that player 1 or player 2 wins, depending on how the board is configured. Now, one of the things I love to emphasize to my students is once you've solved a problem, you can have a few minutes to celebrate, and then you have to move on and extend. And so what kind of generalizations could you give me? How could we generalize?
Based on the chocolate idea, what if we said that anytime you make a small enough piece of chocolate, it just gets eaten and it's removed completely from the game?
So for instance,
Like if you have a 2x2 board, the
Right.
first move, the game is immediately over after that.
so you would say maybe if you create a 1x2 piece that vanishes. So that is a non-standard generalization. That is a much more interesting than the low-hanging fruit. I like this one. So when move, if you create a small piece, say area less than equal to fixed number, that vanishes. So for instance, on a move, I could actually lose 2 pieces if I break things into enough parts. Great tweak. Now all of a sudden there can be a lot of interesting strategy. There is an easier generalization of the game. So I called this a rectangle game in the beginning. How could you generalize it?
Square.
So square is a type of rectangle. So our analysis of the rectangle game would cover if the board is a square. Two different shapes. What if we gave you a shape like this? You know, at Williams College, we don't see this letter that often. But you know, in the olden days, you know,
We're not allowed to get little 50s.
yeah. So what if we have something like this? What do you think? Do you think you know who's going to win?
Even area,
Yeah,
so it's even.
just depends on even or odd area. It's the same proof. Right? Every time we move, we add another piece. You keep playing until there's no chocolate bars left. So the same proof we did before would work here. So this is one generalization. Another one is other 2D shapes. And because of how I've written that, you're hopefully primed for another possibility. Yeah, what if we do 3 dimensions and we have cutting planes maybe? You know, could you generalize this to higher dimensions? You know, what if I gave you a box and you're slicing the box with a knife coming down? Would you be able to analyze something like that? Would it be similar? So the goal is always to try to take something that you can do and have the students push it forward. What I really like about this one is that you gather data. It's not just talking about theory, but there's let's collect some data and let's build some intuition. Let's try to make a conjecture. You know,
It would be a really cool way to visually introduce proof in like geometry class.
yes, because this does not require that much to prove.
No, but it also, it like breaks it down to a very basic level while making, like, I feel like they would feel very accomplished.
Yes, and what's nice is, I think to aid that is they would make the conjecture that they're trying to prove. It's not, and we're reading the book and the book knows what the answer is and we're just following in the book's footsteps. It's this, you're actually looking at data and trying to figure out what should we try to show is true. There's generalizations of this game.
Is it the same for 3-dimensional? Like if I had a 5x3x3, would that be player?
Well, let's think if you cut it in with a plane, what's going to happen? Every time you cut, you add another piece. So it should just matter as to whether or not the total number of pieces at the end is even or odd. In some sense, is the volume even or odd? So all that really matters is as long as one side is even, player one wins. And we could do this in 3 dimensions, and you could actually build something and you'll slice it like that. So I'm going to show you a related game, and no one wants to see all the technical details, but this is actually related to a Nobel Prize in economics.
Cool.
So you're always happy to provide, I'll call it the Sperner game. And the way it works is the following. I'll take a triangle and I will subdivide it into smaller triangles. Now, if I do too many, the game will take too long. All right. And then, in the interest of time, we always assume that I can draw somewhat okay. Oh, no, this one doesn't look right. Okay, there we go. Okay. So here's how the game is played. I start off with, I'm a mathematician, so I count 0, 1, 2. Okay. And if you look, there's a bunch of vertices on this triangle where the lines are meeting. And some of the vertices are on the outside, some of the vertices are on the inside. Every vertex needs a label. Okay, so we label the vertices. 1. Inside, any of 0, 1, 2 can be used. Outside, have to use the numbers from the endpoints. So what that means is, on the bottom, I can only use a 0 or 1 here. On the left side, I can only use a 0 or 2. On the right side, I can only use a 1 or a 2. Okay? And then we have to assign labels to everything else. And your goal, prevent me from labeling one small triangle with all 3 distinct labels. So for example, if I label a triangle 0, 1, 2, then I win. Okay? So everybody understand what you're trying to do. I'm trying to get one of the small triangles labeled 0, 1, 2. You're trying to stop me. Who do you think has the advantage? What's your thought?
You have to.
Why? I'm the teacher. I'm choosing the game. Well, why do you think I might have the advantage in trying to get one of the triangles labeled 0, 1, 2?
Because we're responding.
You're responding, so you move, I move, and I can maybe attack you in multiple places. So what could I do to decrease my advantage?
Let us take all the moves ourselves.
Okay, so that's really generous to give you all the moves, but I could let you have more moves. So I'll do the following. If we, you get n moves per 1 move of me, and you can win this many dollars. So if we go 1 for 1, I'll give the entire class $1. $1 per person, $1 per person.
I
Alright.
said.
Well, you're right, that doesn't seem that much. I'll give you $1,000. All right, $1,000 if you can beat me alternating one move at a time. If you do 2 moves for every 1 move of mine, I'll give you 500. If you do 3 moves for every 1 move of mine, I'll give you 250. 4 moves for every 1 move of mine, I'll give you 125. 5 moves for every 1 of mine, I'll give you, let's keep it simple. I'll give you, how many, 2, we have 6 people here. So the people at home in Zoom, ha, 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 you get nothing for being on Zoom, all right? 6 moves for every 1 move of mine, I'll give you $30. 7 moves for every 1 move of mine, I'll give you 15. And when I was doing this a few years ago with high school students, one of them asked an interesting question that nobody had asked ever before. She wanted to know if they could bank moves. So if you have 3 moves for every move of mine, do you have to make all 3 of your moves at once, or can you bank? Do you guys want to have the ability to bank?
Not on the first one.
Do you want to have the ability, the option?
Yes,
Yes, why?
because you don't have to use
You
it.
don't have to use it, right? Now, with certain people, it's actually dangerous to give them certain things. I don't know if anybody here has ever played the game Mafia or Murder.
Yes.
So when I was in grad school, we played a lot and we created a lot of interesting characters, including the vigilante. So the vigilante is a civilian who can kill at night. And frequently the civilians would kill the vigilante because the vigilante was killing too many civilians. And so just because you have the ability to use something doesn't mean you have to. It can't hurt you from a theoretical point of view of being able to bank. From a practical point of view, if you have people who don't know how to do things properly, it could actually be very bad. So I will give you the opportunity to bank. You do not have to use it. You can choose the level we'll play now. How many moves would you like for every 1 of mine?
One.
So if you do that,
You can't make anything.
you won't have, no, you can even bank your move. You can pass on moving. You can bank 1, but then for every move you do, I get to respond immediately. You will make a lot of money if you can beat me, but I can respond quickly. Shall we?
Let's do it. Why not?
Sure, why not?
All right, so now if I can do this properly,
What program are you using?
I'm just using Keynote. It's basically like a PowerPoint program for the iPad. And so what's nice about this is I can now have all the slides. And I'm just going to create, 2 boards. Okay. And so similar to chess, in order to make things a little bit faster, we can introduce some notation, maybe row A, B, C, D, E, F. So you can just tell me, I want to move second dot row D, and then that way we can quickly understand. Where would you like to go first? And you can bank your first move if you want to give me the first move.
Let's do 0 and the one next to the 0 in row A.
So right here, I am going to, now I could over here put a 1 over here and stop my attack, but I'm going to respond symmetrically. I like responding symmetrically. What do you think? What do you think about my comment?
That you like responding symmetrically.
Yeah. Do you know me well enough to interpret that comment?
Throw us off the
I was gonna say, you could be just trying to trick us.
I could, or I could have been doing that earlier so that when we got to this, my strategy is to be symmetric now, and you won't think that because the last one was, so I'm trying to get in your heads. I love this job. What do you want to do now?
I wanna put a 0 on B, the second one in.
A 0 on B, the second one in over here?
Yeah.
Okay. So now I can be a little bit of a pain and I could attack you by putting a 2 here. Is there a danger of me getting this one and making a triangle? No, because I can only put a 0 or a 2 here. So I would need a 1 if I wanted to win, but I can't put a 1 there. So by putting a 0 there, putting a 2 here doesn't help me. Putting a 0 here doesn't help me. So I will respond with a 1 and start trying to march towards you. So we're going to have 0s and 1s marching towards each other. You see my symmetry strategy?
0 on 1, and then you're gonna try and put a 2 there.
Yeah, and then I can try to be, again, you are always welcome to bank if you want. Where would you like to go next? You get to go or you can bank. So
If we end up with the 0 and 1 like that.
so if you end up with like a 0, 1 over here, I'm threatening you in 2 different ways
Right,
and you're in
that's what I'm
trouble.
trying to say.
Yes. And so don't spend too much time on this right now, or we're not going to get to other fun things. It's okay to spend some time. And again, so just
I want my $1,000.
yeah, not happening.
Yeah.
So there's a line that I didn't show you over here, where you can have infinitely many moves. I get none, and you get $1 million. So what I'm saying is, I will not move at all. I'll give you every move. This is why I'm not worried. It doesn't matter what you do. The game is rigged. So just in the interest of time, just choose some place to move. It does not matter.
0 on C2.
0 on C2. Keep the pattern going. Whoops. Right. You know, you're screwed anyway. I mean, it doesn't really matter. And now I will go over here with a 1, and this will be threatening you in 2 different ways. And what's nice about this is it does kind of look like the symmetry pattern is working. It turns out you cannot win. Cannot stop me. And it is really, it's another parity proof. So again, one of the things I really try to emphasize is that frequently what you want to study is not what you should study first, is you should build up to it. What do you think might be easier to study rather than the triangle game? The line game, right? So let's look at the line game. Try to stop me from getting a 0, 1 line segment. And I'm going to give you 2 proofs that you're screwed. Okay, here's the first proof. What do you have to label this point here? 0. Otherwise, so what do you have to label this point? 0. So you see that as you walk in this direction, everything has to be labeled 0. But what if we go in the other direction? What do you have to label this? 1. What do you have to label this? So you see that as you move in from the right, everything has to be labeled 1. As you move in from the left, everything has to be labeled by 0. What's going to happen? they'll meet. And you'll have to label something both 0 and 1, and it's impossible. So as we march from the left, we see everything has to be labeled 0, or we have a 0, 1 segment. As we come down from the right, everything has to be labeled 1, or we have a 0, 1 segment. So this works, so this is a proof, but it doesn't generalize. And one of the things that's really important to note is different proofs have different value. So I went to a large number of schools in my career, and I was a postdoc at a school that has just won a national title in football. Does anybody know the name of that school? The national title in football. Now, they lost to Oregon in the season, but beat Oregon in the playoffs. Nope.
Ohio State.
Nope, it's not Ohio State. That's not the official name.
Ohio.
The Ohio State University. In mathematics, we don't talk about the proof. We talk about a proof of something. There's more than one way to prove something. Different proofs illustrate different things. And so this is a proof, but this proof doesn't generalize as well. I want to show you another proof and try to tie all the stuff together. So proof 2. And what I want to do is use something called monovariance. These are quantities that only move in one direction. So if you notice in the very first game we looked at, the HersheyBar game, the number of pieces we had was a monovariant. As the moves progressed, we never had fewer pieces, we always got more pieces. So that would be a strict monovariant, it's constantly increasing. Can anybody give me something about yourself that is a monovariant, that only moves in one direction about yourself? Your age, right? As much as we might like, your age is not going to go down. Give me something about yourself that is not a monovariant. Your weight. Weight is the most common one that's chosen. Height is also a monovariant. No. Nope. Sadly, as we get older, a lot of us get shorter, right? Most things change in both directions. It's very rare to have something that only moves in one direction. There's some really nice problems we can do related to this, where the challenge is often figuring out what do you want to study. And this is where it's almost more of an art than a science, trying to figure out what to look at. This is where I think machine learning and AI is going to have incredible impact in society, is they can just try billions and trillions of possibilities quickly. And you don't necessarily need that flash of insight when you can just compute the hell out of the problem. For a lot of these things, if you ever teach geometry, the insight is coming up with, where do I put this auxiliary line? And if you put the auxiliary line in just the right place, the proof proceeds. But how did someone know to draw the line there? So what I want to do is I want to create a monovariant that's going to help me analyze the game. And my monovariant is the number of 0, 1 segments. So when we initially start, we only have 2 things labeled on the ends. How many segments do we start with? So how many 0, 1 segments when only the 2 ends are labeled?
Oh, of the line?
Yeah,
Just one.
just 1. And what kind of number is 1? Odd.
Oh,
So now let's put in a new label. Let's put in a label here. If I put in the label 0, how many 0, 1 segments do we have now? So we have 2 0, 1 segments. Where are the 2 0, 1 segments?
I'm just thinking on either side of 0.
Well, on this side, I have a 0, 1 segment. But on this side, what is it? It's a 0, 0. So that's a 0, 0. This is a 0, 1. So how many segments do we have now? How many 0, 1 segments do we have? Just 1 segment. let's take this point over here. Let's put a 1 here. Now, how many 0, 1 segments do we have?
Oh, no, yeah.
No, 3.
3. This is a 0, 1. That's a 1, 0. But a 1, 0 is really the same as a 0, 1. Right? And then we still have this one. Notice, and again, we don't have a huge amount of data, but what can you tell me about the change in the number of 0, 1 segments when you add a new label? The change in the number of 0, 1 segments when add a label.
Increase by odd value.
Well, we started with 1, then we went to 1, then we went to 3. So what was the first change? The first change was
So what's the next one gonna be?
0. The second change was,
1.
nope, 2. So the change here is no change. Here is a change of 2. Let's do one more label. Put in a 0. Now have, and I'll put in the 0 over here. So now we have this as a 0, 1 segment. This is going to be 0, 0. This is still going to be 1, 0. And this is still going to be 0, 1. So no change. So now I have 3 segments. So what's the change here? No change. So twice we had a change of 0. Once we had a change of 2. What do you think is always going to be true about the change?
It'll either be 0 or 2.
Either 0 or 2. So the change at a label is 0 or 2. That's even. So the parity of the number of 0, 1 segments is unchanged.
What is the word parity?
Means just is it even or odd? So if you started odd, you stay odd. If you started even, you stay even. So whenever we put in a new label, we either have no change in the number of 0, 1s, or we have a change by 2. Let's see why this is true. So let's look at all the possible configurations. I could have 0, 0 with a label in between, or I could have 1, 1 with a label between, or I could have 0, 1 with a label between. What case have I not shown? Oops, there should not be anything here. What case have I not shown? Is there any other possible labeling for the 2 outside vertices?
Out of symmetry.
I'm sorry. Good. So because of symmetry, I've eliminated one label. What's the labeling I've eliminated? 1, 0. I don't have to analyze 1, 0 because that's really the same as 0, 1 if I just reflect. So this principle of symmetry. So for each of these, oh, there shouldn't be a label here yet. For each of these, there's 2 possibilities. So from here, I can go down to 2 possibilities. 0, 1, 0. Actually, let's do 0, 0, 0, or 0, 1, 0. And here, there's no change. And here, it's a change of 2. So we start off with no 0, 1 segments. Now we have 2. Over here, I have 2 possibilities. I could go to 1, 0, 1, or I could go to 1, 1, 1. There's no change if I go to 1, 1, 1. There's a +2 change if I go to 1, 0, 0. And for the 0, 1, there's 2 possibilities. I could go to 0, 0, 1, or I could go to 0, 1, 1, and both of them have no change. So we always change by 2 or 0. So since we started with 1, 0, 1 segment, we will always have a 0, 1 segment. The key fact we're using is if you're an odd number, you must be at least 1. This is a great way to prove that something exists. I show that if I count it, the number of times it occurs is an odd number, and the only way you can have an odd number is to be at least 1. So it has to occur. There's things where I can prove that the number of times it occurs is even. That's not enough to know it exists. But if I know that there's an odd number of them and there's at least, if I know there's an odd number of one, it has to be at least once. So this is how you can prove in the line game that there will always be a 0, 1 segment. I am resisting I am a professor impulse to now go and do the full proof of the triangle game. If anybody wants to, I have videos on this, I have handouts on this, I'm happy to share that. This is not the place to go into that detail. It's enough to just show you that this can be done. And what you do is you look at triangles and you try to find a way to use this oddness to prove that there has to be at least one triangle that's labeled 0, 1, 2. It can be done. You don't need any advanced mathematics. You just need even odd. This is not the place to do this. Okay, I hope you can see though the ingredients that, yeah, I think he could probably do it if he really wanted to. Now, the 0, 1 game is boring, right? Why is the 0, 1 game boring? It's predetermined, right? So fix it, right? Fix the 0, 1 game. There's a lot of great summer programs for talented high school students. And one of them, it's either Ross or Promise, I apologize, I can't remember which. It's prove, disprove, or salvage if possible. And so once you analyze this with the students, okay, we agree the 0, 1 game sucks. What can you do to make it better? You have to change what the outcome is, or you have to change the rules a bit. So maybe change how you determine the winner. So before we said, if there's even one 0, 1 segment, the 0, 1 person wins. And we know there always has to be at least one 0, 1 segment, so the game is boring. So what could we do instead? So one possibility is only win if at least 2 0, 1 segments. And now, if you had every move, could you make sure that there's only one 0, 1 segment? If you had every move, what could you do to make sure there's only one 0, 1 segment? So you get every single move. What can you do to prevent me from getting 2 or more 0, 1 segments? Yes, and?
Put a 0.
Okay, and now what? So I'll put a 0 here, and now what should I go?
I was thinking the other way.
Oh, well, I wrote it here, so. What should I do next? Okay, what should I do here?
I can't.
Oh, sorry. So after the blue 0, what should I put in the next spot?
The one closest to the 1.
Okay, what do you want to put there?
Where
So far left, far right.
far right,
Okay, what do you want to put next to the 1?
a 0,
Okay, and what do you want to put next to that 0?
a 0.
Right. So I was just saying, I just think it makes more sense viewing it starting from the left and just propagating all zeros down. Because you're putting in a 0, 1 already right next to that. And if I ever got to go next, if you put a 0 there, I'd just put a 1 next to it. But I can just march down with zeros, or conversely, I could march down with 1s. And so if I have to have at least 2 0, 1 segments and you get every move, you can stop me from winning. So now the game might be a little bit more interesting. What else could you do? There's no wrong answers. There's
Confused play.
we want to make the game interesting.
Think. Just trying to think outside.
Try to maximize the number of 0-1 segments.
Okay, so related to that, maybe player one gets, let's say, 1 point for a 0-0 or 1-1. Player two gets 1 point for a 0-1 or 1-1. And maybe you deduct 1 point from player two, because we know player two has to get something. So what if we do like this? So now it's every time you have a 0-0 or 1-1, player one is getting the point. Every time you have a 0-1 or a 1, oh, so not a 1-1, 1-0, player two is getting the point. So now each person gets half of the possibilities. Now all of a sudden the game is more interesting. And so, for example, I'll still take the 0-1. So I'll let you go first. Where would you like to go?
Would we be zeros or ones?
Well, you're trying to get 0-0, 1-1. Every time you get a 0-0 or 1-1, you get a point. Every time I get a 1-0 or 0-1, I get a point.
Are we deducting the point from player two?
And we can deduct the point from player two.
So put a zero next to the zero.
So one thing is, if you just put a 0 next to the 0, you've earned yourself a point. Right? And so what do you think I'll do?
Same thing on the other side.
So I could do the same thing on the other side.
Oh, but the same thing.
What if I go,
You put in the next one, then do you get more points?
well, just at the end of the day, you know you're going to get a point for this. Because at the end of the day, that's going to be labeled 0-0. So there's nothing I can do to prevent you from getting that point. I could go here, and that would give me a point no matter what at the end of the day. Now, the question is, do I have a better strategy? What if I go here? Would that be a good move for me?
It's 2, 1, 0, it's 2 points.
I'm sorry?
Wouldn't that
Well,
be-
but it's not at the end of the day. I only get it at the end of the day if they're next to each other, right? So there's all those squares that are going to be filled in. If I go here, where would you like to go on your turn?
I put a 1 between the two.
Yeah, you'd put a 1 between here, and now all of a sudden you've just gotten 2 points. So that would be a really bad move for me. So I probably don't want to put. What if instead of putting a 1, I put a 0 here? Is that a good move for me?
So you get a point of, wow.
Does it matter what is put over here?
No, it's still good either.
What happens if a 0 is put here? What happens over here?
You get a point.
We each get a point. What happens if a 1 is put here?
Each get a
Right, so as soon as I do that, we each get a point. It negates each other. Is there any incentive for you to move there?
No.
Unless you don't want to open something up by moving. It might be useful to have a throwaway move, right? And so what if instead of putting a 0 there, what if I put a 0 over here? You know, I'm trying to open myself up to maybe trying to get things in both directions. What I hope is it's not immediately clear now what the strategy is. And it's good to have stuff like this. It's good to be able to talk to kids and say, we don't know. So I deliberately have not thought about this. I have deliberately not thought about, is there a simple proof as to what the optimal strategy is? Is there a way to respond to something like this? You know, I don't like pretending at the end of the day, I don't know what the answer is when I do. If I'm giving this kids, I don't know what's best. You know, same thing with the reverse tic-tac-toe. I don't know what the best strategy is. Here are just some thoughts, and to me, it's the thought process that matters, is going to the kids and saying, what would you do? What's good about this? What's bad about this? You know, you put that 0 next to the 0 in the beginning, you've guaranteed yourself a point. And then, you know, the question is, can I then start, you know, would I want to put a 1 over here and start threatening? So, you know, this I think is a good place to take, you know, our first break. Oh crap! Oh no, it's just me saying it. Okay. This is, I think, a good place to take a break. The main idea here is this idea of parity, this idea of monovariant, that we often have things that are moving in a certain direction, and we can use that to analyze things very well. All right, so let's take a 5-minute break.